video part 2, double integrals. We were just trying to find the volume of the solid shape over here, the volume of the solid shape under this curve, right? Under this curve, uh, under this Z, right, axis, and x-axis, y-axis. Okay, I was saying that I'll take this as this yellow, the x, and I go up, right? I go up to have the Z. I go up to have the Z as a height, because the height of this yellow shaded, right, is a rectangular shape. Why? Even if this is a curved line, this is a curved line, or all of them are curved lines, but since we are taking just a small part, which is the x, very, very small distance between two different axes, this means we are trying to have the sides, the edges, as much as we can as straight lines to have this rectangle, right? This rectangle, the area of this yellow rectangle is equal to area of yellow rectangle, right? Is equal to simply the width of this yellow rectangle and the height of this yellow rectangle. The width is the x and the height is simply, right? The height is this, which is simply f of xy, which is z, right? So it's f of xy dx, because it's length times width, or width times height, whatever. If I want to have the area of the whole sheet, purple sheet of paper, I will do what in this case? I will do summation of every single like areas beside it, infinite areas, right? But it's not infinite areas, it's exactly from 0 to a, right? The x, the lower the x we can have is 0, which is this one here, and the higher upper the x we can have is a. So it's integral of f of xy from 0 to a, simply from 0 to a. So it's integral from 0 to a f of xy dx. That's great. That's great. If this is the area of the purple sheet only in a 3-dimension, which is 2-dimensional, it's a relation between just z and x. If I need to continue to find the whole volume of the solid body, so I need to put many sheets beside each other, many sheets beside each other, infinite sheets, to have to cover the area, to cover the whole y from 0, from lower bound 0 to upper bound b. So if I take a small change in y, which is dy over here, and I raise it like this, right, to have the z and the x, right? So what do we have now? It's not sheet of paper, it's dimensional sheet, right? 3-dimensional sheet of paper. That's great. In this case, what do we have? We have volume, right? We have volume, which is the same as we did over here, the same as we did over here, f of xy times dx, f of xy times dx, which is integral of this from 0 to 1, gives me all the paper, multiplied by the third dimension I got, which is dy, right? Which is dy. I will have what? Let me do it down here, because it will not be area. So it will be like all of this I got, right? 0 to a f of x y dx, f of xy dx, from 0 to a f of x y dx, all of those multiplied by dy, which is the third dimension. It gives me this 3-dimensional rectangular shape, right? Small dimensions of x and small dimension of y, right? And multiplied by f of xy, which is the height. So it's a matter of just length times width times height. It's the same as what we did over here. Now, if I need all these pieces to be beside each other to cover the whole solid body, right? I will integrate is the summation of all these from this point to that point, right? From lower y to upper y. So it will be from 0 to b, and that will be the volume of the solid body. So we can integrate first in terms of x, and we consider y as constant, and then we integrate the solution, what we got here, integral from 0 to a f of xy dx. We consider it as f of y. Simply, it's f of y. This will be f of y. So this f of y dy, we integrate it with respect to 0b. From 0 to b, it will cover the whole solid body. We can do something else. Instead of doing this, we can do the same thing, but instead of doing that, we can fix a, right? We take a certain a over here, we fix x, sorry, we take a certain x over here, and we go all the way, right? And we need to have this sheet of paper first, this sheet of paper, okay? We can have this sheet of paper. All right, that's great. This sheet of paper has simply, we take, let's start from over here, for example, we take dy, this is dy, and we go up height, which is z, which is f of xy. So this sheet of paper will be equal, right, will be equal, the area of this shaded will be equal to integral, this sheet first, the dimensions of this sheet of paper is dy, this small dy, right, this small dy, multiplied with height, which is z, which is f of xy. And that, if we integrate it from 0 to b, from lower bound of y, which is 0, to upper bound of y, which is b, right, it will cover the whole area of the sheet of paper, and this will be an area, and this will be a function, right, of x. Now, if we want to have this x also as width of this paper, because I'm going to put many papers beside each other, so this will be the x, right, and I go up to have z, and I go to the x-axis, right? This means I will cover this solid, many papers beside each other, right? But it's still small dimension because it's in terms of dx and dy. This means integrate all these solid papers now beside each other, right? Beside each other will give me the summation of them, will cover the whole thing. So it will be, the volume will be integral from 0 to a, all of this, which is from 0 to b, integral from 0 to b, f of x dx, right? F of x dx, which is f of xy dy, all of them dx. Both will give me the same. I will give you a counter example, and we will see that this will give me the same answer. This will give me exactly the same answer. Either we took this or this. We still have one more. We can start, instead of taking z, we can start in the surface, which is xy first, and then we go up high to have the height, right? I'll do it in the next video.